Hello and welcome to my this lecture. Today I'll cover these topics. First one is hardness, another one is creep, and then stress relaxation, then fatigue, and then endurance limit. Let us start. What is hardness? The first topic is about hardness. So hardness is a property by virtue of which metal offer resistance to abrasion or scratch or indentation. Simply write down that it is resistance of material of material resistance of material to abrasion abrasion or scratch. Right. So this is hardness. Now note that in previous videos we had discussed about resilience, modulus of resilience, toughness, and modulus of toughness. Resilience is up to the point of yield point, that is resilience, and toughness is up to fracture point. One should remember these things properly. And now next terminology we want to clear is creep. This is a very important concept. We must remember that from conceptual point of view, the creep is a very practical phenomenon. It is a very practical phenomenon. Creep deformation is permanent. So creep is a deformation which is permanent. Let me draw one diagram. Let this is a rod, right? This is some kind of rod, okay, and some force is applied over this rod, like this P, but the elongation is within elastic limit. Let this is the elongation of this material, right? Now this elongation is del, but this is within elastic limit del. So if I release this load P, then we will come back to this its original shape. However, after a long period of time, there will be additional permanent deformation of material. Let us this one. Let us denote it by del C. Let it be del C. So this particular deformation is because of creep, right? And this particular deformation is known as creep, and it is permanent in nature, right? And if I release load at this time, only this particular deformation will be recovered, but this will be permanent in nature. If I draw it on a graph, this is fixed beam, right? Fixed bar, and on vertical axis, this I draw deflection, and on horizontal axis I draw time, right? So you will see that within elastic limit up to this is within elastic deformation del. This is del, and after that it is like this, right? So from this graph we can see that after a certain deflection del C, after a certain deflection there is not much creep deflection. It will become constant like this. It is approaching to straight line. It is not a straight line, it is approaching to straight line, right? So this particular time is T naught. T naught is a very small time, like 1 second. We applied just within this time, and this particular time you can say T. Now this T time is very much greater than this T naught. So creep occur over a large period of time. So it is very much clear, and T naught is say loading time. T naught is loading time. Why I am taking it as a loading time? Because I am considering the applied load as a gradually applied load, because gradually applied load go from 0 to P in a time T naught, right? So that is why I am saying that T naught is a loading time, loading time, loading time, right? Now you can write down that creep is a time dependent. The first point is the creep is time dependent, time dependent, dependent. Number one, phenomena when load is constant. This load is constant. Load is constant and load is within elastic limit. Load is within elastic limit, within elastic limit. Then further deformation should not be expected, but after a long time deflection is found to be increased. This increased deflection is called creep deflection. So these three criteria needs to be met. If we want to define some kind of permanent deformation has happened because of creep, then it should be with these three criteria. These three criteria should match. It is a time dependent, time should be long, load should be constant, and applied load should be within elastic limit. Then after a long period of time there will be permanent deformation in the material, to which we call creep. Okay, this deformation is plastic in nature, right? And after removal of load the creep deformation cannot be recovered, right? Now what are the factors which affect the creep? What are the factors which affect the creep? Magnitude of load, magnitude of factors affecting creep. You can note down that what are the factors which affect the creep. Number one is load magnitude, magnitude. Number two is type of loading, what kind of load it is, type of loading, that is static or dynamic. We will discuss all these things also in great details. Number three is age, oblique time, means how much time, since how many years the load is applied, like this. Okay, so these are the, another one is temperature. Another one is type of metal. All these are the factors which affect the creep. Now this creep deformation is undesirable, and it is very pronounced, significant at higher temperature. This particular criteria affect the creep a lot. At higher temperature the rate of creep will be much more. When temperature of metal reach half of the melting point temperature, then creep become intolerable. Such a temperature is called homologous temperature. This temperature reach half the melting point of temperature. That temperature is known as homologous temperature, right? Example, there are engines, turbines, right, where temperature of the metal increase, and when it is half the melting point it is known as homologous temperature. From this particular diagram it is clear that rate of creep deformation decrease with time. The rate is increasing because this line is becoming horizontal, approaching to be horizontal line. Slope give deformation with time, which is decreasing slope. So the slope is decreasing. Example are electricity wires. You must have seen that electric wires connected on poles sag after a few years, and creep is more significant than normal loading, right, in wires. So this is all about creep. And you can also note down that certain kind of failures which happen due to creep. Number one failure is, let me clear this, uh, that so the main failures due to creeps are like failure of steam turbine blades, steam turbine blade failure. This is because of creep. Seizing of engine, seizing of engine. This is also due to creep. Similarly, failure of long span pre-stressed bridge, failure of furnace, failure of furnace. Right. All these are the main examples of this failure due to creep. Right. Now, next our definition is what is stress relaxation. Stress relaxation is, one must have seen, it is also related to creep. That this one is a cable, and initially we tight the cable between these two poles, fully tight, and an original stress sigma naught is generated between the in the material, right. Now what happened that after 5 years, initially we generate this much stress in this. After 5 years the stress will decrease like this. Let me clear this. uh, right. So this is stress strain diagram, this is stress, and this is time, stress by time diagram, sorry. So this is the original stress we generated, but after 5 years the stress start declining. This is known as stress relaxation. As the stress start declining, this cable will sag like this. So this particular phenomena is known as the stress relaxation. So the stress in the material is reduced, right. Now next topic we will cover is uh, our this one, fatigue. What is fatigue and how the fatigue works. Next topic is fatigue. When loading is cyclic or reverse cycle reverse cyclic, then in every cycle certain energy is stored, even though stress is below the elastic limit. And when total strain energy stored exceed the modulus of toughness, then fracture and a surface crack will appear on the surface, and such failure is called the failure by fatigue. Based on the practical observation, it is found that if loading is such that stress developed is below the endurance limit, then failure will not occur even at large number of cyclic loading, right. You can note down the definition of fatigue. Now I'll explain what it means. Before, in our, I think, ninth lecture, in ninth part, we discussed toughness and modulus of toughness. Now, what is fatigue? Number one, there is a cyclic loading. Cyclic loading. Now, cyclic loading does not mean plus and then minus. Cyclic loading just mean loading again and again, loading and again reloading, loading, reloading, loading, reloading, loading, reloading. This is known as cyclic loading. This is stress, this is strain. Now, what happens that if I draw the stress strain diagram like this, that this is stress strain diagram and this is point of elasticity, it is like this, right? Now I'll choose a different color for explaining this. Let I loaded the material from this point. This is the point of proportionality. This is the elastic limit. This is upper yield point. This is lower yield point. This is end of yield plateau. This is necking point. This is fracture point, right? I loaded up to this point, up to after elastic limit. This is elastic limit. I loaded up to this point. Now if I loaded up to this point, it will come, if I release the load, it will come back like this, right? So this much strain energy will be stored in the material. This is the area. Now if I again now reload it, I reload it. Let me use some another color, another darker color like this. If I again reload from this point, this is point, original point O, I loaded up to this point, up to this point. After that I release the load, material will come back and this much energy is stored. Now I will again reload up to this point and here I will release the energy and it will come back to this position. Again certain amount of energy will be stored over there. Now again I will reload it and I'll come back from this point, it will come back to this position and again certain amount of energy is stored, strain energy is stored in this material, and I will do this cyclic position again and again. Finally I will reach at a fracture point. This is the fracture point. So when the energy stored is sufficient to make the fracture inside the material, then the material will fail. So what I am doing cyclic loading. First I am loading up to this point, after that unloading, after that again reloading up to this point, after that again unloading, again reloading up to this point, again unloading. In every loading and unloading, certain amount of strain energy is getting stored inside the material, and that when that energy become equal to the fracture strain energy, then the material will fail. This particular phenomena is known as the fatigue. Now, here one important point comes to our notice, that if the stress developed is below the endurance limit, then failure will not occur even at large number of cyclic loadings. If we loaded material but only up to this point, this is the endurance limit stress, loaded up to this point, loaded up to this point, loaded up to this point, then infinite number of cycles, after infinite number of cycle also material will not fail, because there is no strain energy stored in the material, right? That particular stress is known as the endurance limit. For example, for now the concept of endurance limit is also there. Endurance limit for ms mild steel, the endurance limit is 186 Newton per mm square, and for aluminium the endurance limit is 131 Newton per mm square. So endurance limit is that level of stress below which failure is unlikely to occur even at infinite number of cyclic loadings. Example of the fatigue failure are breaking of wire due to cyclic bending. If there is a wire and you first bend it like this and after that you bend it like this, and again bend it like this. So this particular point is coming under cyclic loading of tension compression, tension compression, tension compression. So this is a kind of cyclic loading. Similar failure of a MiG aircraft due to surface crack on the turbine blade or on the wings. Failure of impeller of centrifugal pump are the example of failure because of fatigue. Failure of circumference of wheel is also a type of failure due to fatigue, right? So all these topics are covered. If anyone is unable to understand any of the topics, then please let me know in the comments.